There is a building in Pasadena, California, on the grounds of NASA's Jet Propulsion Laboratory, where a handful of people spend their working hours speaking to a machine that will not answer them until tomorrow. They type a command into a terminal. The instruction leaves Earth as a pulse of radio energy and begins a journey at the only speed the universe permits anything to travel. It clears the moon in a little over a second. It overtakes the sun's light in 8 minutes. It races past Jupiter in under an hour, then past Saturn, past the orbit of Neptune, past the last gravitational handholds of the solar system, and out into a darkness that has no friendly name. After most of a full day in transit, it arrives. The spacecraft is called Voyager 1, and then the people in Pasadena wait again, a second time, for the answer to come back across the same impossible gulf. This is what it actually means to operate the most remote object that human beings have ever built. Forget the movie version, with its glowing screens and instant replies and dramatic countdowns. The truth is slower and stranger than that. It is a conversation stretched across nearly 2 full days, conducted between a team of engineers standing on one small planet and a 30-some kilogram instrument coasting through the space between the stars at better than 16 kilometers every second. Each command carries an uncomfortable weight. Nothing can be undone mid-flight. There is no pause, no recall, no second attempt before the consequences arrive. There is only the arithmetic, the laws of physics, and the quiet faith that a decision made on a screen in California will still be the right one when it lands 20-some light hours away. The numbers help frame how unforgiving the distance has become. Light, the fastest thing the universe permits, still needs the better part of a day to bridge the gap, one way. A round trip burns close to 46 hours. That means a problem the team spots on a Monday afternoon was already unfolding 2 days earlier, by the moment the warning began its journey toward them. They are not watching the spacecraft in the present. They are watching its past, reacting to events that have long since happened, sending help toward a version of the machine that may already have moved on. It is the nearest thing to time travel that engineering has ever asked of anyone, and it wears on a person in ways that have nothing to do with the hours. And lately, the people in that room have not been sleeping well. Voyager 1 lifted off on the 5th of September 1977. It was not the Trailblazer. Pioneer 10 had pushed into the outer solar system 5 years earlier and survived the crossing. But Voyager carried sharper eyes, took a bolder path through the planets, and was sent to do up close what its predecessor had only managed to suggest from afar. The plan was almost modest: reach Jupiter, continue to Saturn, send home a portfolio of photographs, then fade. That was meant to be the whole of it. Roughly 5 years, 2 worlds, a tidy conclusion. The spacecraft never received that memo. When the encounter with Saturn ended, nothing intervened to halt the probe, because nothing out there can. There is no air to drag against it, no nearby mass heavy enough to bend it back, so it simply continued along the line that momentum and gravity had already drawn for it, climbing slightly above the flat disk on which the planets ride, traveling away from the sun and the worlds and every place that humanity had ever charted. Year gave way to year, and then to decade, until the sun behind it had shrunk to a single unremarkable spark, lost among the countless other sparks scattered across the sky. In the summer of 2012, after 35 years aloft, the spacecraft slipped across the heliopause. That is the frontier where the solar wind, the ceaseless outpouring of charged particles streaming from our star, finally surrenders to the cold plasma that drifts between the stars. Inside that boundary, the sun still rules. Beyond it, the sun's reach is finished. Voyager 1 stepped across the line. Nothing made by human hands had ever managed that before. In that instant, it became our first true emissary to interstellar space. It had been flying for 35 years on machinery sketched out with slide rules and fed by punched cards. Its entire memory was smaller than the space a single photograph occupies on the phone in your pocket. And somehow, against every reasonable expectation, it was still working. To grasp the danger now facing Voyager 1, you first have to understand how it keeps the lights on. The answer is not the one most people would guess. The spacecraft has no solar panels, and never did. Out at Jupiter, the sunlight is already 25 times fainter than what bathes the Earth. By Saturn, it has dwindled to roughly 1/100th of its strength here. By the time the probe reached the edge of the Sun's domain, our star had become so dim that even the most capable solar cells ever manufactured would have drawn almost nothing from it. So the designers reached for a different kind of engine entirely. They built the spacecraft around a radioisotope thermoelectric generator, an RTG, which is little more than a carefully sealed lump of plutonium-238. As the plutonium decays, it gives off heat. Clever materials turn that heat directly into a trickle of electricity. There are no pistons, no spinning parts, no fuel tank to drain in the ordinary sense. Only the patient, unstoppable physics of radioactive decay, ticking away across the years. At launch, that generator delivered something close to 470 watts. It was enough to feed a respectable bank of scientific instruments, run the heaters that keep the propellant lines from freezing solid, and power the transmitter that beams every measurement back toward home. But plutonium-238 surrenders half of itself roughly every 88 years, which means the output never holds steady. It falls. A little every year, reliably, without exception. By the time the probe crossed into interstellar space in 2012, a full third of its original supply had already evaporated. As of 2026, it produces somewhere in the neighborhood of 240 watts, less than half of what it began with. 4 watts vanish annually. There is a cruel elegance to the way this plays out. The very feature that made the RTG perfect for deep space, its absolute reliability, is also the source of the slow execution. A solar panel might fail suddenly and be coaxed back. A battery might be recharged. But radioactive decay cannot be paused, reversed, refueled, or argued with. It is the one process aboard the spacecraft that operates entirely outside human reach. Every gram of plutonium that gives up its heat today will never give it again, and the engineers can do nothing but watch the supply ebb and plan around the loss. In a sense, the mission has always been a race against a clock that no one is allowed to touch. It is tempting to wave that figure away as nothing. It is not nothing. When the entire budget you have to work with sits in the low hundreds of watts, and a large share of that must be set aside for the heaters, the radio, and the bare minimum systems that keep the craft from dying, then 4 watts a year forces a reckoning. Each year, the engineers at JPL have to sit down and decide all over again what survives and what is sacrificed. Each year, some part of the spacecraft that has hummed along faithfully for decades is switched off for good. Not because it broke, not because anything went wrong, simply because the cold mathematics of decay refused to leave another choice on the table. Voyager 1 set out carrying 10 scientific instruments, cameras and spectrometers, sensors tuned to charged particles, cosmic rays, plasma, magnetic fields, ultraviolet light. Each was built to interrogate a different mystery about the outer planets, and together they assembled a portrait of the solar system that the astronomers of 1977 could only have imagined. Across the decades, those instruments have been quietly retired, one after another. The cameras were among the first to go dark, shut down in 1990, not long after they captured the photograph the world remembers as the pale blue dot. The infrared instrument followed, then the ultraviolet spectrometer, then more, in sequence, as the shrinking power budget narrowed the list of what the mission could still afford to care about. By the time the probe entered interstellar space, only a few were left awake. And in April of 2026, yet another fell silent. The low-energy charged particles experiment, the LECP, had been gathering data almost continuously since 1977. 49 years of it. Ions and electrons sweeping past the spacecraft at the boundary of the solar system and well beyond, tallied and recorded and carried home across 15 billion miles of vacuum. It was not switched off because it failed. No part of it broke. It went quiet because the spacecraft could no longer spare the electricity to run it. The trouble that set this in motion arrived on the 27th of February, 2026. The team had sent up an ordinary roll command, a small rotation meant to recalibrate the magnetometer. The spacecraft carried it out, but as it did, the power readings sagged in a way nobody had predicted. Not catastrophically, not enough to break anything on the spot, but enough to make the engineers go pale, because Voyager 1 carries an automated fault protection routine that can fire entirely on its own if the available power slips too low. When it triggers, it begins shutting systems down in an order that the engineers neither chose nor can easily reverse, and untangling a self-inflicted cascade like that from 20-some light hours away could devour weeks. So the team chose to move first on their own terms. They sent the command to retire the LECP themselves. It went offline on the 17th of April, 2026. The instruction took most of a day to reach the probe. It took the spacecraft a few hours to carry it out, and then the longest-running scientific instrument in interstellar space stopped speaking. Two remain awake: a magnetometer, reading the magnetic texture of the realm between the stars, and a plasma wave instrument, eavesdropping on the electromagnetic murmur of a place the sun can no longer touch. That is all that survives of a payload that once photographed the cloud bands of Jupiter and the rings of Saturn. There is something worth pausing on in that sequence of shutdowns. The order was not improvised in a panic. Years ago, long before the margins grew this thin, the scientists and engineers sat down together and worked out the painful list in advance, ranking each instrument by how much unique knowledge it could still return against how much power it demanded to do so. They were, in effect, writing the spacecraft's hospice plan decades ahead of need, deciding in calm meetings which of their instruments would be the last to speak. When the LECP's turn came, no one had to ask what came next. It had been settled long before by people who understood that the kindest thing they could do for the mission was to make the hard choices while they still had the luxury of making them slowly. The people at JPL refuse to treat those two surviving instruments as the final word. They have a scheme, and they have given it a name. They call it the Big Bang. The label has nothing to do with the birth of the cosmos. It refers instead to the character of the move itself, a single coordinated reconfiguration of several spacecraft systems all at once, designed to rebalance the power books and claw back enough margin to carry the mission meaningfully into the 2030s. The idea runs roughly like this. Rather than continuing to pick off components one at a time as the supply dwindles, the Big Bang would rearrange a whole cluster of power-hungry devices in a single stroke, trading some of them for thriftier substitutes and shutting others off entirely. The aim is to settle into a new balance point, a configuration in which whatever remains can run for years longer inside the ever-tightening envelope than the present setup could ever manage. But this is not the kind of thing anyone attempts for the first time on a probe 15 billion miles away, where a single exchange of messages eats up the better part of 2 days. So the engineers will rehearse it on Voyager 2 first. The twin launched a fortnight before Voyager 1 in 1977, but took a more leisurely route through the planets, and now sits roughly 2 billion miles nearer to Earth. Its power reserves are a touch healthier, and its signal delay is a little shorter, which makes it a more forgiving stage on which to test something this irreversible. The trials are set for May and June of 2026. If Voyager 2 comes through the Big Bang intact, if its systems settle cleanly into the new arrangement and the data keeps flowing, the team will try the same procedure on Voyager 1 no sooner than July. And there is one small, telling detail. When the engineers powered down the LECP in April, they deliberately left a tiny motor turning inside it, 1/2 watt. It was a choice, not an oversight, because if the Big Bang manages to free up enough breathing room, there is a real chance they could wake the instrument back up. A single resurrection for the oldest science instrument flying through interstellar space. One more window to draw measurements from a region nothing humanity builds will reach again for decades. No one can say whether it will succeed, but the simple fact that the possibility was preserved at all says something about the kind of people who have nursed this mission along for 49 years. What makes the gamble so nerve-wracking is the other danger lurking behind every power decision: the cold. Interstellar space sits only a few degrees above absolute zero, and the spacecraft's delicate plumbing, the lines carrying the propellant that lets it point its antenna at Earth, will freeze and crack if they are allowed to chill too far. So the engineers cannot simply switch off everything that draws current. Strip away too much, and the heaters fail, and the probe dies not from starvation, but from frostbite. Every watt redirected towards science is a watt no longer keeping the machine warm, and every watt spent on warmth is one denied to discovery. The Big Bang is an attempt to thread that needle one more time, to find a posture in which the spacecraft can stay both alive and useful for as long as the plutonium will allow. While all of this plays out on the ground, Voyager 1 never stops moving. More than 10 miles every second, hour after hour, day after day, pressing outward from a star it can no longer truly sense. And in the course of this year, it will pass a marker with no precedent anywhere in the long story of exploration. 1 light day from Earth. A light day is simply how far light gets in 24 hours, a span of roughly 26 billion kilometers. To anchor that against something familiar, the Sun lies a mere 8 light minutes from us. The closest neighboring star system, Alpha Centauri, sprawls more than 4 light years out. Voyager 1 now drifts in the enormous empty stretch between those two markers, a place so distant that even a word like remote feels too small to carry the meaning. When the probe reaches that line, the signal arriving from it at any given moment will have departed a full day earlier. The engineer who sends an instruction on a Tuesday morning will not learn the result until Wednesday. From the perspective of the people trying to keep it alive, the spacecraft lives in a permanent state of yesterday, always reporting on a self that no longer exists. And still, it speaks to us, in defiance of every instinct about what should be possible, across a separation so vast it overwhelms the imagination. A machine about the size of a compact car, running on roughly the processing muscle of a 1970s desk calculator, continues to relay home its readings on the magnetic field of interstellar space, on the plasma waves rippling through the medium between the stars, on an environment that no instrument in all of history before this one had ever measured from the inside. That information cannot be replaced. There is no understudy mission waiting in the wings. There is no second instrument anywhere gathering the same data. The next spacecraft capable of reaching interstellar space and sending genuine science back to Earth remains, by even the sunniest forecasts, decades from launch. Whatever Voyager 1 manages to tell us in these last years is knowledge we would otherwise simply never possess, a hole in the human record that would stay empty for a generation or more. Consider, too, what it takes merely to hear the thing. By the time Voyager 1's whisper reaches Earth, it has spread out and weakened across billions of miles, until the power touching our antennas is almost laughably faint, a fraction of a billionth of a watt. To catch a signal that delicate, the great dishes of NASA's deep space network, some of them 70 meters across, must lock onto a single point in the sky and strain to separate that murmur from the roar of cosmic noise behind it. It is the engineering equivalent of standing on one coast and recognizing a friend's voice carried on the wind from the other. That this works at all, night after night, half a century on, is its own quiet miracle stacked atop the larger one. A last command will be sent to Voyager 1. No one can name the day. The engineers at JPL are bending every skill they have towards shoving that moment as deep into the future as it will go, and they are extraordinarily good at this. The ambition is to keep both Voyager spacecraft working into the 2030s, a goal that looked like wishful thinking a decade ago and now, with the right calls made at the right instance, sits within arm's reach. But the physics does not bargain. The plutonium keeps no promises. Eventually the remaining power will sink beneath the floor required to run even a single instrument, and the science will end. For a stretch afterward, the transmitter will go on broadcasting a bare carrier tone, a signal carrying no message, a kind of electromagnetic pulse with nothing left to say. And then in time that too will sink below the faint background hiss of the universe, lost in the static that fills every corner of space, and the spacecraft will fall silent for good. It will not stop traveling. Nothing out there exists to slow it. In something like 40,000 years, it will drift past another star, a dim red dwarf catalogued as Gliese 445, sweeping within roughly 1.5 light years of it, before the two paths peel apart once more. By then, whatever civilization may stand on Earth, if any still does, will share nothing meaningful with the one that built this probe. No one will be waiting for its signal. No one will recall the room in Pasadena where people once sat at their consoles and counted off the hours until a reply arrived. Only a frozen relic from a forgotten age, carrying a gold-plated copper record stamped with music and spoken greetings in 55 languages, gliding through the dark at 16 kilometers a second toward no particular destination. But that day has not come. Today, there are engineers walking into JPL before sunrise, writing instructions for hardware assembled before most of them were born, running their simulations for a maneuver they have nicknamed the Big Bang, aimed at a spacecraft 15 billion miles distant. Today, Voyager 1 is still tracing the magnetic field of interstellar space and sending the numbers home across a distance that makes the word home feel almost unbearably small. Today, it has not gone quiet. Today, the signal is still arriving. A faint voice from the very rim of everything we have ever touched, and we have not stopped listening.